So here's the expression for the voltage outside of a point charge. So if I have a point charge here and we want to know the voltage at some point X marks the spot, that would tell us again the energy if I put a particle here some distance away. And so what I want us to do is work a little bit more with this voltage to get a sense of how we might use it to calculate the voltage for other kinds of charge distributions rather than just one charge. And we did this before, and I think it's useful to do the same sort of setup. So we can do this sort of setup where we have 3 particles all a distance a away. And I know you're thinking, oh, we're going to get to the semicircle and the integral. And you're right, we are going to get there. But this is a little easier to work with. So I have 3 charges, all Q, and the X marks the spot is right at the origin, and they're all a distance a away. And so the voltage at the origin, at 0, 0, where there's no particles, is just equal to, we just add these up, no vectors. So it's 3 kq over a, because they're all kq over a, they're all the same distance away, so there's 3 of them. Done. That's pretty easy. And if we add 2 more particles, so if we make it 5 particles, 1, 2, 3, 4, 5, then of course instead of a 3, this becomes a 5. Right? So this becomes, this voltage with 5 particles now becomes 5q kq over a. So that's pretty straightforward. So now we're going to look at, with that sort of in mind, we're going to look at this same semicircle that we did before. Right? So here's our semicircle such that it is. There's our distance A over here, we'll make that theta. Okay, so sort of do that. And if we look at then, again, a little bit of Q, right? This is what we did before. There's our little bit of Q, dQ, and we want to know the small contribution to the voltage right at that spot. So dV is equal to K dQ over A. So our voltage would just be the integral of this, integral dV, which would be equal to the integral of K dQ over A. K is a constant, A is a constant, so this just becomes K over A integral dQ. Now before, when we were doing this, we had an integral that had a Q and a theta, and we didn't know what to do with it. Here, it's really straightforward. Integral of dq with nothing else is just like integral dx. It's x, so it's total q. Done. Okay, so maybe I'm convincing you voltage is kind of a nice thing. I hope. I mean, electric field is perfectly nice also, but voltage is in fact a nice thing, and it's a really nice way to look at things. Now, we know that, so sometimes it's easier to get the voltage. This is clearly easier to get the voltage, right? At this point. It's not so easy to get the voltage, say, at this point, though, because everything's a different distance away. So I don't want to convince you that it's always easier. I mean, at this point, it's hard to find the electric field, and it's hard to find the voltage, which is why I didn't pick that point. But in general, if you have an expression for the voltage, because our voltage is this integral minus integral E dot dr, since voltage is the antiderivative, it shouldn't be a surprise that we might be able to get to the electric field from the voltage. Now the problem is this is a vector and this is not. And so the way we get around that is we can say that the electric field in the x direction is equal to minus the derivative of the voltage with respect to x. And I didn't make this quite like a regular d. This is called a partial derivative, which sounds really fancy. And it kind of is, but really it's an easier derivative to do. It says take the derivative of v with respect to x and let any other variable be constant. So if this v is an equation of x and y, you treat y as a constant in this. And then the electric field in the y direction looks like minus dv dy, and in the z direction it looks like minus dV dz. So this is how we sort of unpack this and go from an integral form, an antiderivative form, to a differential form, if you like. Now, we typically aren't going to do these derivatives, but these derivatives can kind of help us, give us an idea of what the electric field looks like if we know something about what the potential looks like. And so I want to talk about something called an equipotential surface here. So if we have a positive charge like this, and we want an equipotential surface, what that means is we want to know a distance, something where the potential is the same everywhere on this line, or an equipotential contour, if you like. You can think of it as a contour in a drawing of a series of mountains, for example, when you look on a flat map and you see lines that tell the elevations. So this should be centered on this. If I'm the same distance r away, then every point on here is going to be the same potential, right? So say that I've got, I don't know, a Q of, let's say K times Q is equal to 10, whatever that is. And so R, if R is equal to 1, then this would be 10 volts here. And then when R is equal to 2, this would be my equipotential, if it's circular, of 5 volts. Just to pick values, okay? So each circle tells you that you've got a constant potential. So this is fairly straightforward when we've got just charges, a charge or two, and we can draw the equipotential contour. But we can also measure the equipotential contour, so you can set up situations where, for example, you have something that's an, I don't know, like 12 volts or so, and then you have another conductor. So this is a conductor at 12 volts. And this is another conductor that, let's say, is at 0 volts, then you can map out, just by using a multimeter to map out your voltages, you can actually map out the equipotential lines. And so what you could do is when you're close to this, like that's maybe the 11 volt line or something like that, but the 1 volt line tends to kind of go around like this. This is maybe the 2 volt line coming around like that. And 3, so forth. And so these sort of spread out. These are the equipotential lines. Maybe this is 1 volt, 2 volt, and 3 volt. And what we can do is see where the lines are crowded together, where we have a big change in the x direction, let's say in the x direction, a big change in voltage over change in x right here, that we're going to have a really strong electric field. Because we have a big dV over this dx range compared to over here. And so we can start to get a picture, and actually this should be symmetric. It shouldn't be spread out so much more here compared to here. But this can start to map out our electric field. It runs perpendicular. That's one of the things that comes out of these equations. It runs perpendicular to the contours, right? So the electric field runs like this. Or it could run the other way. But in this case, it's always going to go to the lower potential, right? So it's going to go like this. That would be your electric field, and it sort of goes like this and like this. And so this is, these are your electric field, your equipotentials. So the idea is that everywhere along here is about 3 volts. You're this far away, you're this close to the 12 volts. And then everywhere along here, it's fairly constant. And so you can actually see that high points like this have pretty strong electric fields. And sometimes this is where you can see, like if this is a lightning rod setup, you can actually see the beginning of a strong enough electric field that you start to break down air, and you can get some crackling in the air sometimes there if you've got a pretty high potential, not 12 volts, but many thousands of volts in a cloud way up high. You don't want to actually be there at that point because then you're going to have some lightning and it's going to hit this spot. This is a spot where the electrons are really going to want to go here, as you can see, because we've got a really strong electric field there.